This is all about getting started with SOLIDWORKS and 3D Experience simulation solutions. And I'm going to do kind of an introduction and a little overview real quick before we turn it over to our main presenter, who is Jon Duffin. So when we talk about simulation tools, they're scattered throughout the product line, and there's just a whole bunch of different levels. So just kind of visually speaking, if you have SOLIDWORKS Standard, you do have some very basic simulation, SimExpress and FlowExpress. If you have SOLIDWORKS Premium, you've got some more advanced simulation capabilities, specifically structural FEA, which we're going to cover today, motion analysis, which is kinematic and dynamic. And then if you need to expand upon that, there's the sliding scale. You can go up to simulation standard, professional, or premium. With professional, you get a lot more additional types of studies, things like optimization, thermal frequency buckling, some really powerful welded connectors, things like that. And then once you go up into the premium, that's where you're talking about hitting things with bats, taking things beyond yield, permanent deformation, complex, carbon fiber composites, you name it. And we also have, in another kind of parallel track, we have a flow simulation product. This one doesn't have as many levels. It does have a couple of add-on modules, but I believe Jon's probably going to show us some of this as well, because there's a lot of fluid flow and structural analysis type of applications that people are going to need to see. But the big takeaway here is that it all builds upon itself. Everything you learn, all the work you do is going to be able to build. And for example, fluid flow and pressure distributions will be able to be carried over to a structural analysis. It all works together. So whatever your challenges are, we should have something to meet your needs. And in fact, it's a very scalable simulation. What we're going to talk about is today is getting started. And a lot of times getting started means you're going to be doing the basic stuff, simulating early and often. So as a designer, you're going to be checking to make sure that everything's going to be strong enough early in the design before you have the tooling costs and the costs of ECNs and things like that. But as you get more further down the process, you get more complicated systems. You may need to sort of continue to scale, and that's where we go past simulation premium. We can even start to go on into the 3D Experience platform and to Abacus Desktop. So some really powerful tools. So let us know where you need to be, and we'll kind of let you know where you need to go and what you need to do to be able to get there. So I'm going to turn it over to my main man, Jon Duffin. He's going to show us all about the SOLIDWORKS and 3D Experience simulation.
My name is Jon Duffin, and I'm one of the simulation experts here at MLC CAD Systems. And I'm really excited to talk to you guys today about simulation. Simulation absolutely blows my mind in what it is able to do. Back in the world of doing all your hand calculations and spending weeks, if not months or years doing calculations is really behind us, where if you know some good theory, you can run a lot of simulations on your own. So I'm excited to show you. So let's dive right into it. So in this webinar, we're going to be talking about three main packages of SOLIDWORKS simulation. Now, we won't be able to go in depth on all of them, and there's some that we won't even cover at all. But what we're going to cover in this webinar is doing a brief overview of SOLIDWORKS Simulation Standard. Then we'll talk about some of the studies that we can run that's involved in Simulation Professional. And then the last part of the webinar, we'll talk about SOLIDWORKS Flow Simulation and the kind of stuff that you can do in there. So without further ado, let's go ahead and get started with SOLIDWORKS Simulation Standard. So what I'll go ahead and do is I'm going to open up this assembly that we have. Now this is a pretty cool assembly. It is some mining equipment, so it's a big piece of machinery. Let me see there, but just to kind of give a little bit of background in it before we go into the simulation portion, is that over there on the left side, you have that big boom and that big hunk of metal getting out there. So that hunk of metal is a big drill that can drill in mine shafts to drill holes, and then also it can insert rods into the walls. And then also you'll see that other boom over on that same left side is there where it has that mesh. so it can apply mesh to the interior walls of the tunnels as it mines. So pretty cool equipment, but also you would, as you may guess, it is very critical to make sure that each of these parts does not fail. As you're in the middle of the mine shaft, doing maintenance in the bottom of it can be very difficult, and just for the overall integrity of the model. So for this, we're going to go ahead and look at this boom assembly here. So we can see that's highlighted in blue, and I'm going to go ahead and open that up in its own window. And this boom has some hydraulic pistons that are on there that drive that big drill and rod assembly. So as you can imagine, it needs to withstand quite a bit of force for what you're doing. And for the sake of this demonstration, we're just going to analyze a small part of this, but you can't extrapolate these ideas to bigger assemblies that you're doing. So the part that we're going to look at in this case is going to be this Knuckle Kit. So this attaches to the piston rod and is going to withstand most of the force that these hydraulic pistons are going to do. So I'm going to go ahead and open that guy up, and we'll start a simulation. So in SOLIDWORKS Simulation Standard, the main type of study that you can run is a linear static study. Now this type of study gets most people by, and even if you're going to be running deeper analysis in the future, you always start with the linear static. Now the main assumptions with linear static is that your material's linear, linear behavior and what it does, which most metals and a lot of your common engineering materials are, but if you're going more into rubbers and things like that, then that would be nonlinear. And then also that you're going to have small deformations. You're not applying so much force that it permanently deforms, and you want to see that there. And then also the other assumption that the forces on here are applied slowly over time and you aren't doing dynamic effects, which there are other modules within SOLIDWORKS to do that, but within the simulation standard, those are the assumptions that we have for our linear static studies. So very first, when you set up a study, you can utilize the power of SOLIDWORKS CAD to set up your analysis and change your part to get ready for simulation. And that's one of the powers of integrating simulation within CAD, is that you can easily go back and forth and set up and run studies a lot faster than you would any other way. So what I'm going to do for this study, so we can see down the middle there is a line of symmetry. In this model, it won't make a huge difference in the solve time, but to kind of show just the process, I'll do that. And there's a few things we want to set up. So right now this isn't fixed, so I'm just going to go ahead for this study, say this is going to be a 35-degree angle. I have set up a angle mate from before that I'm just going to unsuppress. And then I'll go ahead and create the symmetry. So for this, I'm going to go ahead and just add a FEA configuration, finite element analysis, and then just use your typical SOLIDWORKS CAD to start this geometry. So I'll make sure that this is in the center. Do a cut extrude, do 3R both, confirm that. Okay, and like that, with our model, we are ready to start a simulation. So within here, once you have the SOLIDWORKS simulation module added, you can just go and click a new study, and you'll see lots of different studies that are in this list. Now I'll talk a little more in depth about some of these other studies and how they are available, but within the SOLIDWORKS standard simulation, this linear static is the main study that you'll want. So I'll go ahead and confirm this, and we can see still within the SOLIDWORKS interface, we now have some simulation parameters over here. Now you do need to know some theory behind the scenes and stuff in order to evaluate if results are good, and that's what some of our training classes are for. But through this, you'll see how easy it is to set up a simulation and start getting some results for your own. So you can basically just work down this property manager here. So first we look at our parts. We can see that there's several different parts in this assembly, and it automatically pulled in all the materials from that were applied on our part level just back in SOLIDWORKS. So that's cool with being able to integrate it with SOLIDWORKS. You are able to manually change this, but that's where it starts with that. So with parts, we're all good. Materials are assigned, so we can go on to our next one. Connections is how these parts interact. Now there's all sorts of connections that you can do in SOLIDWORKS Standard. You can model springs, pins, bolts, bearings. things like that. Some of these, like welds, would be available in higher licensing of simulation, but most of your standard ones that you are available to you in this. So in this case, our interaction is just in between opponents pushing up against each other. And we can have a global interaction. So basically, it's if you don't specify how these components are going to act, here's what's going to default to. And so right now it's set to bonded. So basically all these parts, just like it's acting like it's one part that's bonded to each other. You can do contact, which basically makes so they can't penetrate through each other. In this case, in real life, it's probably more of a no penetration or a contact condition. But due to the nature of the setup, your results are actually really similar and you have less time for solving with bonded. So we're going to go ahead and do bonded just for the sake of this webinar. So these are bonded together. So you're good for that. You can go here and calculate and see how these automatic connections are being calculated. So we can see all these red is where it's going to be bonding these parts to each other. So you look at that, the different parts, okay, everything looks like it's bonding as expected. So you can work your way down the property manager. Next is fixtures. You need to fix it in place somehow, else when you apply force, it's just going to have nothing to react to that force with that. So I just go ahead, right click, fix geometry. In this case, because this pin is connected to a big bracket on the other side, so we can assume that that bracket is significantly more stiff than this model is going to be. And so we're going to apply our fixture to that side. And here, that bracket also comes and sits on top of this plate right here. So we're going to assume it can't move up through it, but it can slide if needed. So we're going to use roller slider and you kind of see how it constrains the part and apply it to these bottom faces. Now the last constraint that we need to do is the symmetry constraint. So we need to select all these faces that lie on the symmetry plane to do that. So I'll go ahead, I'll just filter for faces just to make it quicker. If there was many more faces than this, I'd probably, I accidentally selected an extra one there. I'd probably use some selection managers to be quicker, but in this case, we're about at that number. That's probably just as quick to just manually select them. So with that, we can go ahead and we see, yep, all our faces that are on that symmetry boundary. Go here, apply symmetry, and this makes so it will take less time to solve, but still get the same quality of results. So I'll wait for that to calculate and then go ahead and confirm that. And then the last thing that we need to add to set up our study is our force. Now those hydraulic pistons, they can take they have a ton of force in order to lift that beam. So it's about 180,000 newtons per cylinder. In this case, we have half our model since we're using symmetry. So I'll go ahead, and you can see just in a few clicks, I go there, normal to face, half of the 180,000, and we'll do 90,000. And just like that, your basic study is set up. So you can see that applying fixtures, applying some of your setup, it can be very simple and can go very quickly. The next part of this is the mesh. Now, anyone that's even somewhat familiar with finite element analysis, you know that mesh is very important for your analysis. So in this case, we're just going to start with the default basic mesh to see what kind of results that we can get. And so we can see just with the default of just running it, that it's a relatively coarse mesh, but it's solving the parameters of the stresses at each one of these nodes that are in this part. So generally you want to have it as coarse as possible while still having converged results. So generally that means applying mesh controls, so you selectively get finer mesh in different areas, but we don't know exactly where it's going to be right now. So just like that, we can run the study and start getting some results. So this should only take a few seconds to run and calculate in this circumstance, but once it's done, we'll start seeing some plots immediately that we can start gathering information from here. when you do mesh convergence, generally your stresses always go up as you converge it. So you know, like right off the bat, if your stress is too high, a design changes in order. You can quickly get results so that you can not waste time outsourcing this to other people, or you can quickly just have your designers change it at the same time they're doing simulation. So we have the results. Right now we're looking at displacement plot, which we can quickly animate to see like, okay, and this is an exaggerated deformation of what's going to happen, but you can use this as a gut check. Okay, did I set up the study right? Is the forces in the right spot? Is the, based on the fixtures I have? And things are looking good there. And I'm going to go ahead and just hide this symmetry. Just to make it a little clearer what's going on. We have our stress plot, which this one's von Mises, which is the most common type. And because there's different types of materials in here, the von Mises isn't as important as it would be the factor of safety of what the yield strength of this material is compared to the von Mises stress. But if we go down to factor of safety, it calculates that for us. So we can see right now that the min factor of safety is about 1.7. And I'm going to go ahead and change the scale on this so the max is about 4. And that gives a better to see where our areas of concern are. So we can see our highest levels are in this corner here, and then we have our max down here. Now let's say your company decided that you needed a factor of safety of 2 in order to have it be a valid design. So right now, right off the bat, you see it's 1.7. This isn't valid. This isn't going to work. So you know that design changed in order. And this is where one of the power of SOLIDWORKS simulation comes in, is that you can utilize the CAD interface to change your models and then run your simulation again very quickly. So just like this, I can go down to model. I'll go ahead and change this fillet to make it a little bit bigger and see if that can help with some of the stress. So it's at 10 right now, but I'll go ahead and change that radius to 30 and then rebuild it. So still got our design intent, but we have a little more material there to give us a little more strength in that area of concern. So we can go back to our static study, and we'll go ahead and run this study. And it remeshes it since the geometry changed, and then here in a second we'll see it start solving. Alrighty, and just like that, we can get some more results. I'll go ahead and go to our factor of safety plot, and we can see with that right off the bat we see, okay, our factor of safety is a little over 2. We know when we converge our mesh that stresses will go up a little bit until it's converged, but we can see just quickly how quickly it is to change the geometry and get results. So this is the primary studies that you can run in SOLIDWORKS Simulation Standard. It's honestly what a lot of studies that people need to run. For there are a lot of static parts that you need to determine if it's going to break, what changes are needed, and with SOLIDWORKS Simulation you can get done fast, and you have your same interface, so even if your designers are trained properly, that your designers can also be your simulation specialists. And that's one of the powers of SOLIDWORKS simulation. So with that, we're going to go ahead and talk a little bit about SOLIDWORKS Professional. So this gives us access to some deeper level of studies that allow us to do more with SOLIDWORKS simulation. So I'm going to go ahead and I'm going to click this new study. And right now we ran the static, but when you get SOLIDWORKS Simulation Professional, you're able to run all these different types of studies except for the linear dynamic and the non-linear studies. And those are going to be the highest level package of your SOLIDWORKS Simulation Premium, but we won't go into that detail now. But basically, it is available if your designs need that. So in this case, there is quite a few different studies that are available in SOLIDWORKS Professional that honestly are relatively simple to set up just with taking our course that's a couple days long. Then you can feel pretty confident setting up most of these studies. But a lot of them are very critical to your designs. So some of them here we have a frequency analysis. So this analysis, you can basically import some of your setup from your static study and determine the natural frequencies of your part. Now this is important because if the vibrations that are caused on the part get close to those natural frequencies, it can cause those parts to fail prematurely. And you obviously do not want that to happen. So determining what the natural frequency is and making sure that motors or other things are not running at that speed, or you need to change your design to make so it can withstand those. So a pretty simple study to run, but very important for results. Related to that, we also have buckling. If you have long, slender, narrow components, and this is available in Simulation Professional, and this determines if buckling is going to be a failure prematurely. One that's available actually in SOLIDWORKS Simulation Standard, but also Professional, is your fatigue analysis. So your fatigue, you take in your static study, and it can withstand this once, but you're going to be loading it however many times. Can it withstand it after so many loads of cycling? Within Professional, you also have thermal analysis, so you can do the thermal transfer between solid bodies. What you're doing there, the math behind the scenes is pretty much the same as it is with static. It's just thermal in what it has there. And then you do have some specialty simulations down here. Submodeling, if you ran a simulation on big assembly, then you can section it down to take in the results from your bigger model and then do some mesh refinement and some deeper analysis on smaller parts. Drop tests, understanding how your parts are going to withstand if they're dropped from certain heights and if they're going to break with that. And then a pressure vessel design module. And then the last one here that I'm going to quickly show you how to set up is a design study. Now this is a really cool study because it allows you to automate the design process with utilizing CAD and SOLIDWORKS simulation. So basically you take in your static study, tell it what parameters can change, which dimensions can change, can the material change, and you choose what are your constraints. The stress needs to be below this level, the factor of safety needs to be below this level, your frequency needs to be below this level. And then you have it decide what design is best. You say the best design is the one that weighs the least, which generally equates to cheaper to manufacture, assuming similar geometry. So I'm just going to quickly show you how simple it is to set up a design study. So I'm going to go ahead and just create a design study. And you add variables, constraints, and goals. Variables is what can change. So in here, I have a few parameters set up. So one of them is the flange thickness, which if we zoom in on here, is the thickness of this part. And it comes out at an angle, so it changes also the thickness of this end bracket. And then this is the parameter that we changed from before, which is our fillet size. So those are two that we have set up. So for our study, I'm going to go ahead and add both of these. You can say, okay, it can range between these two values, and I want you to create an experiment to determine which value is best. So for our fillet size, we're going to go ahead and say it can have a minimum of 5 millimeters, and let's go a max of 30. And then for our flange thickness, we're going to go ahead and have a low of 20, and then a max of 45. Okay, constraints. What needs to be true for this to be a good design? So you can add simulation data directly. So I'll go ahead, simulation data, and then factor of safety is what we decide need to be below 2. And so factor of safety, I guess it needs to be greater than 2 to be safe. Okay, and then from here, a goal. So if any designs multiple will have factor of safety over 2, what's going to be best design? In this case, it's going to be the one that weighs the least. So mass properties, and that's going to cut down costs and cut down manufacturing costs generally. So got that, mass, and we want to minimize it. So just like that, you've set up a design study, which you run. It basically creates a design of experiments and runs that analysis. In this case, I think it will run it 10 or 15 times and tell you what design's best. It will take a minute to run, so I won't run it in this webinar, but it's just like that. You can do it. So simulation is incredible. For companies that aren't using it, it is one of the biggest concerns that I've seen is, oh, we don't have specialists in order to run it, or we need to hire a person with a PhD to do it. Which, if you're getting to very high-end simulation that's simulating car crash or whatever there, you probably need to do someone with a PhD. But for most of your designs, what you're doing at your company, most people can do it without having that level of skill. Honestly, a lot of people, if they come and take our training class, which is 3 days to learn your simulation standard products and then another 2 days to go over some of the simulation professional ones, a lot of people can get up and running and start evaluating if they have good results with them. So it is absolutely incredible. All right, so with that, we're going to switch gears and go right into SOLIDWORKS flow simulation. Now, unlike structural simulation where you're analyzing the stress and if things are going to break, in flow, like the name suggests, you're analyzing flow. Now, there's lots of different applications that our customers use for this. We can use to analyze the flow over electronics enclosure to determine if it's cool enough or if it needs more airflow. It can be used to evaluate HVAC systems, see how effective they are and how comfortable people will be in different environments. It can be used to do airflow over objects to get drag coefficients, see how aerodynamic parts are. It can be used for water flow through pipes or valves. And with that, you can even export the forces that are acting on those pipes or valves and export those back into SOLIDWORKS simulation to analyze if they're going to break from those forces. So lots of different applications that can be used. But for SOLIDWORKS flow simulation, there's only one type of license. For simulation, you had your 3, but for flow, it's just the flow. So I'm going to go ahead and show you how to set up a quick study just to show you how quick it is to set up studies and how intuitive it is to be in your SOLIDWORKS interface with this. So I'm going to go ahead and open up this manifold. So what we're going to do is we're going to go ahead and analyze this manifold to determine the airflow through this. So this is our inlet over here on the right. And then for this design, we want the air to be relatively the same going through each of these valves. So we're going to use flow simulation to determine this. So to set up a study, it can go pretty quick and it is intuitive, especially after a little bit of training, just like SOLIDWORKS simulation. But I'm just going to go ahead and activate our flow simulation tab here. And then once that pulls up, I can go ahead and go to flow simulation and I can start a new study. So I'm going to go ahead and use the wizard to do it and just walk through some of the parameters that always need to be set up, even some of the most experienced users. This just helps make it go faster. So flow sim, we can start with our units that we're going to use. The analysis type, we can do internal or external. In this case, since we're concerned about the flow inside this pipe, it's going to be internal. But if we were concerned about the flow once it exited these openings, or if it was getting a drag coefficient around an object, then you would do external. Some of these other options that are available, you can factor in the heat conduction that come from solids. If you're worried about time, just not the steady state solution, you can calculate that. You can factor in gravity, free surfaces, and things like that. From here, you can choose your liquid that you're going to use or your material. So what we're going to do here is just air. There's a pretty good database that just comes with SOLIDWORKS flow simulation, but you can add your own custom ones if you want. And then from here, some of our wall conditions. With here, we'll assume that these walls are smooth. And these are just some of our initial conditions. And with that, we've started our study. Now, from here, because this is an eternal analysis, it needs to have a closed volume in order to then set our parameters of where flow comes in, where it comes out. So it automatically recognizes that, hey, this is enclosed, there's openings here, you need to put some lids on these things to start analyzing. So to make things easier on you, there's a Create Lids tools that helps with planar openings. So I can go ahead and just click all these openings here, and I'll wait a second between each one for it to process. And it creates bodies automatically that then seal this part up. That way then we can add boundary conditions to these faces to determine what the flow is through this part. And like I mentioned with SOLIDWORKS simulation, it is amazing how you just get to stay within your SOLIDWORKS simulation interface, so it becomes a lot more intuitive to learn, and you can go back to your SOLIDWORKS model to make changes if needed. So with that, I'm going to go ahead and create our lids. And now we'll have a enclosed part that we can start doing some analysis on. So just like SOLIDWORKS simulation, we have our feature manager over here that goes through some of the properties that we can set up. Now, some of these you don't use every time. Most of these we won't use in this example here, but depending on your study, there's a lot of options available to assist you in your setup. So in this case, we're going to put a mass flow rate through here, and then these are all going to be open for air, and we want to make sure that the results converge so we get accurate results of the mass flow rate of the air coming out of these openings. Now, to make these faces easier to select, I'm going to go ahead and section view this model and go over here. So very first, we're going to go ahead and set up a boundary condition of saying, okay, on this inlet face, let's do a mass flow rate of air since we set that up in our initial wizard setup. And let's say it's going to be 1 kilogram per second. And now in all these other faces, it's going to be just open to the environment, open to air. So I'll go ahead and insert a boundary condition there, environmental pressure, and then I'll go ahead and just select each one of these. Alrighty, and so we have our inlet, we have our outlets. Pretty simple. The only other thing that we need for this study is determine what we want to solve for. Now the goals, just make sure that it converges those goals so that those specific parameters have accurate results. So I'm going to go ahead and insert a goal here, and I'll use our same environmental pressure faces that we selected before. And then for here, we want this to solve for the mass flow rate. So I'll go ahead and select that. And just like that, our setup for the study is complete. From here, just like SOLIDWORKS simulation, you do mesh the part. It's a different kind of mesh, but it's the same basic ideas. So on here, I'm going to go ahead and edit some of the options for the global mesh. So it's on 3. I'll go ahead and put it up a little bit for what we're doing for here. And then I can just go ahead and run the study and see what some of our initial results are. So we'll see this dialog come up, and it will first mesh it and then run the study. But it is absolutely amazing how quickly we're able to set up a study. For simple studies, obviously very quick. For more complex ones, it can take more time, but still being in a familiar environment makes it a lot easier than it could be. So with here, I'm going to go ahead and insert a goal plot. So these are all our mass flow rates out of each of those openings that we set up. And it's calculating the values as it goes through, and it just wants this to converge so we get an accurate value as it comes. So we'll watch this go along. We can see as it achieves each goal, and it's almost there. And then with that, our calculations are complete. So with that, I'll go ahead and turn off the section view, but I'm just going to go ahead and make this transparent and show some results. So one of the first results that I like to set up is our flow trajectories. Now this is a cool visual one that you can set up, and I'm going to put this on our inlet mass flow. So with that, I'm going to go ahead and show. Okay, we see the small spheres. I'm going to go ahead and make that a little bigger. And then for our input here, I'll go ahead and just do velocity for our coloring. Now, this is a great check. Just like in SOLIDWORKS Flow Simulate or in SOLIDWORKS Simulation, how you very first do your animation of your part to make sure you have your setup correctly. This is a similar setup to be able to just quickly verify that you have things set up. So I'm going to go ahead and just animate this. And you can see aspects. So, I mean, just initially, you've already gotten some good results here that you can see quite a bit of flow through this back one, and it seems to get a little bit slower as it goes through, barely anything in this one. And then a decent amount of flow through this first one, probably due to that churn at the beginning. So just like that, you've gotten some results. But then you can look at more specific items. We can go into our goal plots and look at the actual values. So here's our mass flow rate through each one of those openings. So you can see right now it's not very even. So you know that design change is needed in order to change either the angles of these or how it's set up to better get your results. If you are interested in learning more about simulation, getting demos, or taking our training, please reach out to us and we'll be happy to assist. But thanks for coming, and I hope to talk to you guys again another time. Have a great day.